Now that you've learned a little bit about atomic theory and atomic structure and then what these little atoms are made out of, let's do a little bit more in-depth analysis and talk about the masses of these atoms. Okay, so here's the deal. Every single element in the periodic table is made out of atoms, but not all of these atoms look exactly 100% the same. Okay, you have these things that are called isotopes. And so what happens in an isotope is you have the same number of protons, but different numbers of neutrons. Okay, so in other words, every single element in the periodic table has a characteristic number of protons. Number of protons has to stay exactly the same. If you change number of protons, you change what it is. Okay? In other words, every element has its own atomic number, which is number of protons. But just because the number of protons has to stay the same doesn't mean that the number of neutrons has to stay the same. Okay, that can change. And so that's why the same element might still exist with different isotopes. To try to distinguish between these different isotopes, we say that they all have different mass numbers. Okay, so the mass number is what the total number of nucleons is in that atom. Say, wait, what the heck's nucleon? Okay, fancy word. Nucleon is just something that lives inside the nucleus. So the things that live inside the nucleus are protons and neutrons. Okay, and so different isotopes have different nucleons in them, different numbers of nucleons. And so what we can do is talk about what the average is of all of these different mass numbers for all the different isotopes in an element. And we're going to call this average the atomic mass or atomic weight. And it's actually not a simple average, but a weighted average. And what I mean by a weighted average is we're going to try to incorporate what the fractional abundance is, meaning how popular are these isotopes. Okay, some of these isotopes are far more abundant than others, and so they're going to contribute a lot more to the atomic mass or the atomic weight. So before I give you an example, let's talk about carbon. Okay, carbon is arguably the most important element in the periodic table, so much so that an actual unit of mass is based on isotopes of carbon. Okay, and so there's one isotope of carbon called carbon-12. Carbon-12 has in it 6 protons and 6 neutrons. So imagine taking these 6 protons and these 6 neutrons and putting them all together. Okay, the mass of the proton is not exactly the same as the mass of a neutron. They're close, but they're not exactly the same. So we're going to add these 6 protons and these 6 neutrons together and get 12 total nucleons, and then divide this by 12, and that's going to be equal to 1 AMU, or atomic mass unit. Okay, so 1 AMU is by definition 1/12 of the mass of one single atom of carbon-12. So now that you know that information, let me show you how you can calculate the atomic weight or the atomic mass of carbon by looking at the different mass numbers of all the different isotopes, as well as all of the different fractional abundances for each of these isotopes. Okay, so here's how we're going to do it. Carbon typically exists in 3 different isotopic forms. There's carbon-12, carbon-13, and carbon-14. So these 3 numbers here represent the different mass numbers, or the m sub i's in that equation from before. So each of these mass numbers has a different presence or abundance in nature. Okay, the fractional abundance of carbon-12 is about 98.8%, which means that the vast majority of the carbon on Earth is carbon-12, right? Almost 99% of it is carbon-12. About 1.1% is C13, and a mere 0.1% is carbon-14. So these here represent the different fractions, or f sub i's. So what we're going to do to get the atomic weight, or the atomic mass, is just multiply all of the different fractional abundances by the corresponding mass numbers, and then add them all up. Okay, and so for example, if the mass number is 12, the fractional abundance is 0.988. That's 98.8% expressed as a decimal. And then the second fractional abundance is 0.011 when the mass number is 13. And the last one for carbon-14 has a relative abundance of 0.001. If I multiply all these numbers and add them all up, I get 12.011 AMUs. Okay, and so the point is that I can say that the atomic mass or the atomic weight of carbon is 12.011. So if you look in the periodic table, every single element in the periodic table has a characteristic atomic weight or atomic mass. And that number represents a weighted average of all the different isotopes scaled by their appropriate abundances or fractional abundances. Most of the time, there's one isotope that by far dominates all of the other ones. Okay, so for example, in the case of carbon, you saw that 98.8% of it was carbon-12. So even though the atomic weight or the atomic mass of carbon is not an integer, right, 12.011, it's pretty darn close to 12. So for the interest of saving time and making things a bit easier for you, on the CLEP exam, for example, you can typically round off and just say that the atomic weight or the atomic mass of carbon is approximately 12. Right? It's not exactly 12, but it's pretty darn close to 12. So that is a little tip to make things a little bit easier for you as you take your exam and prepare for the CLEP.